assignment is already violating a clause. Another thing you can do is imagine the following thing. Suppose I have this PRQ, not P. Let's say. Then I get to resolve and say Q. It's resolution. You agree? This, by the way, is called unit resolution. Normal resolutions can increase the length of the resolvent. Because if you start with a 5 clause and a 7 clause, you can get a 4 plus 6, 10 clause. Unit resolution, one of the clauses is exactly length 1. Then the resolvent will basically cancel that part with the other guy's equal, the opposite literal, and then the class size will reduce. Imagine while you are checking these assignments in the middle, not only are you checking whether the clauses are violated, you're also doing this theorem proving in the middle. You're basically proving additional theorems. If this and this is true in this branch, the following additional things will also be true. So even though you haven't actually, if in fact you have PRQ true and you just went to a branch where P has been set to false, then even though you did not consider Q, in essence you have considered Q. Because Q has to be true now. Do you see what I'm saying? This kind of reduces search even further. And this idea actually is called, in CSP terms, it is called forward checking. Okay, it's described here more slowly in this place. But I won't show you right now, but I want to just show you the example here. And say that forward checking improves the search speed even more. Okay? And the general CSP heuristics would be doing forward checking and also doing variable ordering. Which variable to consider at the top of the tree, which at the next layer, which at the next layer. The general CSP rule for it is whichever variable has the smallest domain, you consider that first. My example for that is, imagine you are trying to call Bill Gates and me to a party at your home. One of these days you should do it, right? And you're trying to figure out the day to hold the party. And if we both don't show up, the party can't be held. Now you have to ask me as well as Bill Gates which days were available. Who are you going to ask first? How many people said Bill Gates? They're all failing the class. But really, you should ask Bill Gates. Actually, Bill Gates, when I started this example, Bill Gates has stuff to do. Maybe you should ask me now because I have more stuff to do than him. But in general, he's a busy man. He may not be available. So you might be only saying, on a leap year, February 29th, the next leap year, February 29th is the only day I'm available. Then you come and ask Rob, because Rob is available all the time. The party is coming. You see what I'm saying? So in general, start with the variable with the smaller domain first. That's the variable ordering heuristic for CSPs. This isn't particularly useful in Boolean CSPs because the variables have size 2, have size 1 or size 0 domains. So if you have a size 0 domain, you do it first, otherwise size 1, otherwise size 2. It's not as effective there, but that's the same idea you'll wind up using. Okay? So that's one thing. The other thing I want to show is, this is basically what's called the systematic, this is what is called the, where did I go? Yeah, systematic search, this one. Okay, it's basically CSP systematic search. One of the advantages of CSP is if you find me a world where all clauses are satisfied, any such world is equally good as a solution. You agree? Right? It's like any day when both I and Bill Gates are available and you are available, it's a party. Right? There is no difference as far as you're concerned. We are basically, when I give a domain, all of those days I am available. So the interesting question then is, you don't actually have to do search like this. You don't have to start with one variable, put its value to be true or false, and the other variable. In A-star search, we did this because the path is ultimately the solution. Here, path is not the solution. Essentially, the assignment of variables to values is the solution. The order in which they were assigned the variable values doesn't matter. Which means you could have just said, to heck with this, I will start doing a much simpler search, which is this. Imagine there are n variables. There are only 2 power n solutions possible. Right? Because these are Boolean variables. There are only 2 power n solutions possible. Pick one at random. So randomly said P2 true, Q2 false, R2 true, blah, blah, blah. So you have an assignment. Start a loop. And in the loop, check whether the current assignment satisfies all the constraints. If you're the luckiest person on earth, it may. In which case you say, Mom, I'm done. This is the assignment. If not, I have an assignment that's violating some number of constraints. I need to change the assignment so that fewer number of constraints will be violated. So which direction do I change the assignment? What am I sounding like? Gradient descent. Or hill climbing search. Okay? So essentially what I do is these are a bunch of variables and I need to consider changes. I'll consider local changes. Local changes to assignments. So I get to, because they're Boolean assignments, I get to flip a variable. The question is, which variable should I flip? So I will consider all the variables one at a time, see how many constraints will be violated still after flipping that variable. Pick the variable that will leave least number of constraints violated after flipping. Greedy as hell. Do you see what I'm saying? And then you flip that variable. Now you have a new assignment. Do this all over again. Do you see what I'm saying? This is hill climbing. In CSP terms, in SAT terms, this is called min conflicts heuristic. And the only difference from the simple gradient descent is this. Rather than always be greedy, you take a probability P. With probability P, you do the greedy thing. With probability 1 minus P, you just pick a variable at random. Another of the ideas that we kind of did. If you do this, in essence, the ability of this min-conflict search to find the solution increases, the probability increases. Notice that this is purely local search. The amount of space it is consuming is 1. The one assignment. Any given time it has just one assignment. That's what it's looking at. Do you see what I'm saying? To understand this, you have to understand how to make the tree, how deep is the tree, what is the forward checking, what is the minimum domain heuristic, etc., etc. To understand this, you say flip, flip, flip. Nobody thought this will work. Around 92 time frame, people by mistake actually implemented it and found that most of the Boolean satisfiability problems, and these are not just textbook problems. As I said, airline scheduling can be, some kinds of scheduling problems can be converted into Boolean satisfiability. Sudoku can be converted into Boolean satisfiability. You know who is the biggest consumer of Boolean satisfiability? The thing down the road in Chandler, Intel. Circuit verification is Boolean satisfiability. I don't know if you notice, circuits are Boolean. That's where the whole Boolean logic thing came out. They're like extremely crazy. So in fact, I and my wife keep our marriage by not reading the same papers. And for first time we almost had a big problem was she started reading satisfiability solvers improvements, which was being done by people from verification community. I said, hey, that's my papers, why are you reading? But it turns out they are smarter in that particular case, they come up with a fast follow. Okay, so they have instances of these hard to solve satisfiability instances, and then they would try to just use this GSAT. This one basically was, its name was GSAT and WalkSat. GSAT is the greedy SAT, that means it always does the greedy thing. WalkSat basically does the greedy thing with probability P, and with 1 minus probability 1 minus P, it does the random thing. And the climax for the non-extended session is that they found that this dinky little algorithm was solving much faster these huge problems. And so people felt really, really sad because we wasted this much time doing all this systematic search and local search was doing fine. And the second part of the climax that actually leads her to the next part is they found they couldn't even find problems that this guy can't solve. You see what I'm saying? They actually thought every random satisfiability problem they made, randomly generate, you can randomly generate clauses, randomly, you pick random number of variables, generate clauses randomly, and try to solve it. Okay? They found every possible randomly generated satisfiability problem is solvable in sublinear time. And yet you guys told us that it's co-NP complete. We just proved 1 equal to 0. That's where we will end, and then we'll do the extended part continuing of that. So people have to do it. So we were in this situation where essentially people were finding that all random SAT problems could be solved by this dinky little algorithm. And there were no hard problems. So where are the hard problems? Right? This is the ifs and ands where the wild things are. So where exactly are the hard problems? It's a beautiful idea, and that's actually where phase transition comes from. Okay? So here is an idea. Consider the following thing. A random, we will basically, by the way, it turns out that all SAT problems are thought of in terms of the length of the class. Okay? So you basically think in terms of 3 SAT problems. 3 SATs are all SAT problems where the class length is exactly 3. Some of you may have heard 3 SAT, not heard Boolean SAT. Apparently that's one person told me this. Okay? So 3 SAT is as hard as Boolean satisfiability. So in fact, any Boolean satisfiability problem can be converted into a 3 class length Boolean satisfiability problem. Okay? So that reduces the number of knobs we have to play with. Each class is length 3. So I just have to pick a bunch of variables, let's say 15 variables, bunch of classes, let's say 100 classes, and generate classes randomly. Pick randomly variables, put into the classes. And some will be positive, some will be negative. This is just generation of problems randomly. Okay? And then when they did this, basically they found for the random satisfiability problems, most of the problems they are generating randomly are extremely easy to solve. Why is that? Turns out it's not surprising. First of all, do the Kernel analysis. Consider this magic parameter, number of classes by number of variables. Okay? Number of classes is the constraints. Number of variables is the propositions that they have to that have to satisfy the constraints. Okay? Consider the ends. So number of classes by number of variables can be close to 0 or close to infinity. Okay? So if it is close to 0, if it is, let's say it's in the infinity side, that means you have way too many classes and very few variables. Way too many classes and very few variables. Okay? So I'm trying to have a party with 3 people. These 3 people have a million constraints about their availability. What is the possibility that I can actually have a party? 0. There are only 3 people. They have too many constraints. Do you see what I'm saying? So the probability that you will be able to find the party, find a satisfying assignment for a problem where the number of classes by number of variables is closer to infinity is 0. Right? You understand that? What about this end? If you have number of classes to number of variables, so in this particular case, I am actually considering, so number of classes, okay, actually, in fact, there were 2 things that you should have seen. That's okay. So how about the time taken to solve this problem? When there are 3 people, 3 million constraints about their availability. How long would you think you would take before you realize there can't be a party? You just have to essentially take a pair of classes and say they're mutually inconsistent. Do you see what I'm saying? The moment a pair of classes becomes mutually inconsistent, all classes have to be satisfied. Since a pair is inconsistent, you're dead. So you would be actually able to solve this extremely hard problem very easily. By just say, can't be done. Do you understand what I'm saying? So the time taken to solve this end is close to 0. The probability of having a solution is also close to 0. On this end, the number of classes by number of variables is close to 0. That means there are no constraints compared to the variables. That is pretty much any day everybody is available. Just a second. Okay? What's the probability that you can find a party date? Very high, 1.0. How much of a search do you have to find the day where the party can be held? Very little search, because pretty much any day you pick, everybody is available. Right? So on this end too, the difficulty of the probability that you have a solution to the problem is 1, and the difficulty of solving the problem, the time taken to solve the problem, is close to 0. You see what I'm saying? Now, it's not surprising. This is the game I play. If I make this course so hard that there are 18 projects due every week, you will be done very fast. You would have dropped the course the first day. I won't have anybody to talk to. You see what I'm saying? On the other hand, if I say this course is just fun, you won't drop the course, you have nothing to do either. Again, the amount of time you spent on this course will be close to 0. Whether the course is extremely easy or extremely hard. In the case of extremely hard, you give up. You take something else in your life. The idea is to kind of make your life just miserable enough, right, that you don't ever feel like dropping, but you spend time on the course. That's how you learn, I'm sorry. You understand what I'm saying? It's a design consideration. So this much is not surprising. You should really be surprised at this. You may not have thought about this, but now that I explained, it's not surprising to you that in both ends, the problems are easy. Highly over-constrained problems are easy to solve because they won't have a solution. You can say they have no solution. Highly under-constrained problems are easy to solve because anything is a solution and you can say that is a solution. The difficulty in life is in the middle. This much is understood. This should not be surprising. Okay? So you would think that as the this particular ratio, number of classes to number of variables, is changed from 0 towards infinity, the probability of finding a solution starts with 1, slowly kind of goes down to 0. If I said this, you shouldn't be surprised. And also you should be surprised that the cost of solving it increases, kind of reaches a peak somewhere in the middle, sort of like this course, and then slowly starts coming down, because people will start dropping. This part you should not be surprised. Do you understand what I'm saying? This is first order stuff everybody is supposed to understand. Although you're surprised because I made you feel as if you're surprised, but you shouldn't be surprised. The mind-bending thing is if you were to do this actually empirically, it looks like that. So the cost of the probability of finding a solution would be close to 1 up until some point when it drastically falls, almost like a mirror image sigmoid function, and becomes 0. And the cost of so this is the probability. The cost of solving the problem is pretty easy most of the time. Raises very fast in this extremely narrow region around some magic number of number of classes to number of variables. And then again falls to 0 and nothing happens. Now, if you're picking random problems, what is the chance that you will pick problems in this area if you didn't know this theory? Very low. Most of the time you will be picking problems in this area, if you just randomly generate. And so you're thinking all problems are easy to solve, what's the big rush? SAT is very easy to solve. Do you see what I'm saying? When is the last time you saw this kind of a process, this sort of a crazy thing? So when you start heating water, at any given temperature, some of the water molecules want to become vapor molecules. They get out of the liquid and become vapor. It's happening all the time. That's called evaporation. As you increase the temperature, more and more of the molecules want to become vapor. Not surprising. What is crazy about water is at exactly 100 degrees, everybody wants to leave. Like everybody. That's what boiling point is, in case you've forgotten. At the boiling point, the temperature remains at 100 while the entire water is trying to become vapor. It's called phase transition. You just saw a computational phase transition. Okay? You saw a computational phase transition. So what is the boiling point for these SAT problems? It turns out it's at this point and it's about 4.3, which is the number of classes to number of variables. In case it all looks like it's made up, okay, so these are some actual examples. It's from the original papers showing how random problems look like. And this was some quick implementation of the same thing. Okay, again, for each value of gamma, which is the number of classes to variables, you generated 200 random SAT instances, and you solve them, and you consider the average probability as well as average cost of solving them, and you drew this curve and notice how it looks. This is phase transition. And it turns out that many computational problems actually have this phase transition property. Basically blows your mind, right? And that's why I wanted to point that out, that this is actually possible. In fact, finding that is actually exactly equal to 4.3, empirically pretty much everybody found it's 4.3. You can run this, you will find it. Okay? Doesn't require like TensorFlow. Okay? It's just basically holds, it's a pretty robust result. But showing that it's actually some number next to 4.3, and if it's math has any way, it will have something to do with root pi and cube root of e and all that stuff. Nobody has still shown how to find that particular threshold. These are essentially called sharp threshold phenomena. Okay? Crazy enough? Okay. So the last thing that I want to do in today's class, as much as I can do, maybe I'll do a little bit of it again next class. I want to show you a way of using a propositional logic to represent child generator function in A-star search. So you basically said there are operators that are applied to the state to give new states. So I can think of them as actions, and you have a state, the agent has a state of the world, it takes an action, and it gets a new state. This is what we did in like MDPs too, right? Except the transitions there were on atomic states. State was a black box. S15, you apply this, you will get with this probability S75, this other probability S95. And if I'm looking at just deterministic case right now, then you apply this action to S15, you will get S75. What I want to do is think in terms of states with internal structure, states with feature representation, which you did in the case of reinforcement learning, except you didn't use them because essentially you're just learning the policy directly. Okay? So if you have a Boolean feature representation, here is a very simple example of a world that I'm representing here. It's a blocks world. It's a bunch of blocks that I get to stack on top of each other. And I represent them in this particular propositional thing. Notice that I'm writing it as if they are actually predicates on table with parenthesis A, on table with parenthesis B. But as far as you're concerned, you can think of this as on table dash A, on table dash B, which will be a proposition name. It turns out much of everything that I'm telling you here can just essentially be understood in terms of propositional logic. Okay, so I basically assume in this representation that initial state is represented in terms of some states. Every state variable for the domain, I have to give a value for it. Is it true or false? So if I have only two blocks in the world, and I only care about whether the blocks are on the table or on top of each other, then I need essentially these kinds of variables. On table A, on table B, clear A, clear B, and then I'm trying to put block on top of other block, so I have a robot hand. So I'll say that hand is currently empty. Okay? And then of course if it is empty, that means it's not holding A, it's not holding B, etc. etc. So the initial state essentially is supposedly a complete state. That means it tells you for every proposition making up the state representation, it tells you whether it is true or false currently. That is what it means to say I have full observability. I know the state of the world completely. Okay? And in the goal state, I don't have to tell you everything. Just like I said, just pass the exam. I don't care what shirt you're wearing on the day you're passing the exam. So goal state, I just tell you the variables whose values I care about. And the rest I don't care. So in this particular case, the variables that I care about are goal state is not clear B. That means I want to start from this state and B should not be clear and hand should be empty. Let me ask you first, can you visualize this? So basically here A is on table, B is on table, okay? And A is clear, there is nothing on top of A. B is clear, there is nothing on top of B. Robot hand is standing like this. I want to be in a situation where B is not clear, okay? And you can almost see how this world works. I mean, you have to put somebody on top of B such that it becomes not clear. And hand should still be empty. So to actually go from that state to a state where these goals are true, one sequence that will work, for example, is you take the empty hand, pick up B, put it on top of A, and you're done. What? So pick up A, put it on top of B, and you're done. Right? It's a little plan. It's a very small domain, and it's a plan. Okay? And if you understand how to search for this, you can search for much bigger plans. Basic idea. Okay? So the way you will write the actions, basically it's an obvious way, right? In the sense to want to be able to talk about a pickup action, it will pick up a block as long as hand is empty. That means in the state before the variable hand empty is set to true, and that block itself is clear, and that block is on table. Okay? And in which case, after you pick it up, you're holding that block is no longer on table, hand is no longer empty, and X basically is not clear because it's being held. So I just wrote what the action does to the state. It's the same way, like for example, there is unstack xy. To be able to unstack xy, x should be on top of y to begin with. X is on top of y. I should have a free hand. Hand is empty. And since I'm trying to unstack x, there should not be anything on top of x. Clear x. You see what I'm saying? And then effect is holding x. You're holding the x because you just unstacked it from from y. And not clear x because you're holding it. Y no longer has x on top, so y becomes clear. Hand is no longer empty because it's holding x. This is basically like for your 15 puzzle, you have to write the child generator function, right? You wrote a piece of opaque code. Here you are writing a bunch of actions in terms of the state variables and addition and deletion and changing the polarity of the variables. So this is state variable algebra. Okay? And so if I'm going to search on top of this, if I want to just get the goals, right? Yes?
Is it necessary to have all the features in the discrete format?
In this particular case, yes. This is a discrete, just like it's a propositional logic. Propositional logic is discrete. It's true, false. Okay? So if you try to search on this, if you search this particular problem that I gave you, by the way, since I said initial state is completely known, then I can use what's called closed form assumption. If I know the whole state, then I know. So for example, if I can always check whether people are here in the class or not, if I can completely observe the people who are in the class or not, then if I just give the list of people who are in the class right now, I have also told you the list of people who are not in the class. Because I'm able to see everybody. If on the other hand I only look like this, and I said, yeah, I see some number of people, and those are in the class, then there are some other people who are in the class, I didn't notice them. So then I can't, that's not going to allow closed word assumption. Closed word assumption means what I said is true is the only thing true, everything else is false. Okay?